Hello everyone, and welcome to a momentous day here in the UK. I'm not referring of course to the referendum, but to the latest in the iFormulate Introduce series of webinars entitled today Powderology, an Introduction to the Mysteries of Powders. My name is David Calvert and I'll be your host today. But your main speaker is going to be Ian Jolliffe, who's an associate of iFormulate. In today's speech you'll be hearing some introductions. We'll be talking about what are powders, then Ian will go into some of the challenges, some of the measurement and control, and some of the conclusions. This webinar is being recorded and will be made available to you and your colleagues who maybe haven't been able to make it today. You'll be sent a link to that webinar and to a PDF of the slides in 24 hours time. You are at present all on mute, but we would welcome your questions, and you can use the question function or the chat to function in GoToWebinar, and we'll try and get to as many of those at the end of this session. We will, however, be aware that plenty of people have got limited time, so this webinar will finish after approximately 30 minutes. So before we move on to the main event, just a little bit about iFormulate. We formed iFormulate in 2012, myself and Dr. Jim Bullock. And we've got between us now over 50 years of experience in chemical using industries. You can see in the blue box there some of the areas where we have some experience, and where we don't have some experience we've established a wide range of contacts and network of associates, and among those is our main speaker today, Ian Jolliffe. The services from iFormulate are, we divide them into three strands. We have iFormulate Consult, which is something I'm going to come back to at the end of this webinar. In terms of iFormulate Strategic, we've conducted some strategic work for a number of organizations around formulation. We helped the Knowledge Transfer Network with some of the background work to the National Formulation Centre, which was set up over 12 months ago. We've also helped the Royal Society of Chemistry to look at the use of open data and formulation, and we've also helped Scottish Enterprise to map out their formulation skills. We also do a strand called iFormulate Skills, where we run training courses on our own or in conjunction with partners. Most recently we ran an inkjet formulation course, and Ian today will refer to a design for formulation course which we ran 2 days in 2015. But moving on, it's important to, before you hear every speech, to think, well, is this relevant to me? Well, powders are actually used in a whole range of formulation industries, so pharmaceuticals, healthcare, home care, cosmetics, inks and coatings, agrochemicals, plus probably any other formulation using industry you wish to think of. You may say, well, I don't sell a powder if you're making a formulation. Well, you may not, but you may well use powders as a raw material. They may well be used as an intermediate, so you may take a powder to make a granule that you then make tablet. So powders are extremely relevant, and it's very important that you understand some of the basic properties of what's going on with a powder. So at that stage I'm going to stop speaking and hand you over now to our main speaker, Ian Jolliffe. Over to you, Ian.
Thank you, David, and good afternoon, everyone. This is a webinar on a few basic thoughts for formulators on powders. Let's start off by thinking about the state of the various states. And so we know all about liquids, and I guess we know all about solids, and then there's gases, we know all about those. And then there's these particulates, or powders as we call them. And when particulates are dispersed in liquids, we call them suspensions. And if you've been on the webinar a few months ago, there was a suspensionology webinar, and I think David's team have organised a one-day course recently. But if particles are dispersed in gas, which is usually air, we would call them powders, and usually these particles aren't well suspended and they drop to the floor, and so there's a little pile of powder. And there's various things we want to do with powders, and when we're formulating products, we may just put them in a packet and sell them, or to make them to granules or tablets, might pack them into unit doses so it's nice and easy for people to use. So it might be capsules or bespoke containers. So part of this is how do you meet the challenges of these formulation formats when you're using powders. As David mentioned, we've done a webinar and a course about design for formulation in the past, and talked about how important it is to build in quality from the design stage, knowing exactly what you're making and why you make it. And that also involves a step of actually understanding and putting in place the appropriate controls to achieve the product that you've actually promised to your customers. And I think, you'd all say that most products start with at least some ingredients that are powders, but we know that powders are often difficult to handle, either in processing or as the finished products themselves. They're often dusty, they don't always flow, they're often unpredictable, and they can be affected by environment like moisture or things like that, and also the surfaces they come in contact with. And this dust business, is actually used as a product claim now on Muesli. I've put a little photo I took where I found a product that actually says, "Look, no dust from Muesli." So next slide. Of course, as formulators, we wouldn't just do look, there's no dust. We'd actually think of a better way. So the best way to keep dust out of your Muesli is probably to make something like granola, where you actually stick the particles together into agglomerates that all flow very easily, probably pretty homogeneous, and all the dust is mopped up. Or better still, you can actually stick them all together totally into one sort of dosage unit. So you have a unit dose of Muesli in a bar. It's nice and easy for people to use. Right then, now, so going back to thinking about product states or material states, we can have a state of a solid, and if you stood a weight on a pile of concrete, a set pile of concrete, it would just sit on the top. But if it was a bucket of fluid like water, then obviously the weight would sink to the bottom. So where do powders feature in this? So we had a bucket of powder, and it says maize starch. I don't know if you can see that bit on the screen. The bottom of the slide has fallen off mine, but it says a bucket of powder maize starch. It just looks like that. If you add the weight to that, it disappears, but really it is there. And in this next photo shows. So the volume of powder appears to have increased, but the weight's gone down and pushed it up. So it's not at the bottom or not at the top. Right. But not all powders or groups of powders behave in the same way. So this is our maize starch again, but if it was like pea gravel, then we'd see a different thing. So the weight can actually sit on the top of these. So that's because the particles can easily flow over each other. They're large particles with a smooth surface that fall. So generally we can say that powders made of larger particles are less compressible and flow better. So that's a basic thing that to get across. Right. So what state are powders? I've touched this already. That they're particles dispersed in gas. Generally, the gas is air, but they're also under the influence of gravity and interparticle forces, especially fine particles. And the particles will have to slide past each other, so you can see this particular friction can play a part. We know, because I've shown you just now, that powders can pack down and exist in different volumes or porosities, so they can have different amounts of air between the particles, and they're able to stay in that state for quite some time. And they can flow, but we don't know an awful lot about that. And powder flow was recently described by a speaker at the Academy of Pharmaceuticals and Sciences Symposium as the missing link in the evolution of powder characterization. So even after many, many years, we still struggle to measure powder flow easily. But there are actually more challenges with powders. There are many products that are just one component, and so you have to mix the powders together, the particles together. You aim to mix them to get uniform. So that's one thing. How do you get that uniform in the first place? And then, having got a uniform mix, how do you stop it separating again? And, I talk a bit about muesli, but you open a box of muesli. If you've got a plastic bag inside, you can see all the nuts and fruit at the top, and the wheat flakes or whatever lower down. So it's actually easily separated, and it's a good idea to do a travel test if you're ever going to make anything like that. The other challenges are like surface moisture absorption, which will change the flow properties, surface charge, and if you've weighed out carbomers, you know that if you put some on your spatula and as you approach the balance, you get a little rainbow of particles flying through the air towards the balance because the particles are so charged. Then there's stability. So vibration and gravity will cause particles to pack closer together when they're stood in. And such that the interparticular forces for fine particles in particular make it difficult to induce flow again. And if you have minor moisture content changes, and it might just be surface moisture, the cycling of humidity can melt these into a solid cakes. And one of the first factory trials I did, I was amazed. It used an ingredient called pulverized sucrose, so it's very fine sugar. When the operators put this sack on the ground and then beat it for about 5 minutes with a large mallet before he put it in the mill, because it was just set into one big lump. Then the other stability issue is this segregation. So whether during processing or handling of the powders, it causes particles of different sizes and or different shapes to move at different rates and causes separation. I'll come back to that a bit more in a minute. And you know, factors such as density and surface roughness also play a part there. And particles can be charged, and that can actually cause segregation as well. Right. So, why are different powders? Why do they behave differently? Well, they can have a difference in particle size or particle shape. They can have surface effects, as I mentioned, moisture, but they could be other adsorbed materials, so they can have different charge and different roughness. So if you're developing a product, it's the first step to me is to understand what you actually want from your powder. And you want to make a product that actually fulfills the promises made to your customer. So you want to understand what you need your powder to do. So you need to think about what material attributes are critical to the performance of your product. And we use this phrase, critical product quality attributes. So the things you might consider are flow, which could be particle size or shape, packing properties, which we measure by bulk density, and segregation propensity, which you might use to try match sizes or match shape or density again. And the surface characteristics I mentioned previously. So those are some of the things you might try and measure as material attributes. But you can't measure everything, and it's really important to actually consider what things are actually critical to your product and in the application and in the process. So the customer promise, just to go back to that, this is what we tell the customer what the product will do, and that might be the basis of what we've done, promised through market research, or maybe the business case, or it might just be your internal customer, the factory. So it's the basis really of these critical quality attributes, and along with any industry or regulatory standards that need to be met. So the sort of things you might think of are sensory feel. So if you have gritty, so products might be gritty if the particle size isn't carefully controlled, and you can think of cream cleansers where if you have large gritty particles, that's going to scratch surfaces in your kitchen or bathroom. If it's an oral suspension and you have large particles, obviously that's going to be a bit crunchy in your mouth and not be very nice. And skin creams, obviously you don't want to have that too abrasive. Or it might even just leave visible residues. Rate of solution is another thing where you want the, if it was a pain relief tablet, you'd want the active ingredient to dissolve quickly. Or it could be something like, I was trying to think of examples, and I thought of wallpaper paste, because I can remember in my youth that you had to make it up in a bucket and leave it overnight while it hydrated, these large particles hydrated, but now you can mix it up and use it almost straight away. Separation, well, that's another thing to think about. There's an expectation amongst consumers or customers that the product is the same every time you use it or every time you take a sample from it. It's not the first the first spoonful you take out isn't full of one component like currants, and the last component is all rich in wheat flakes. So neither spoonfuls is as intended. And of course, for certain products like medicines, that could actually be critical. And then there's processability, and that affects our external customers, because if something doesn't process well and we go out of stock, that's not good news. And our internal customers, the factory people, we go to formulators, no time at all telling them what they think of your abilities to formulate things. Next slide, please. So what determines material attributes? Which material attributes are critical to your product? What needs to be controlled? So it's everything that would affect the critical quality attributes of the product, which may be manifested through critical effects on the process. So you need to think carefully what these might be. Particle size is a general one, and there are many situations where you wouldn't want to know what particle size, where you wouldn't want to have particle size controlled. It might affect the release of an active ingredient through dissolution. Now, obviously, larger particles of paracetamol or ibuprofen would take longer to dissolve if you're looking for a fast-acting pain relief tablet. And larger particles have a smaller surface area, so they may not pick up so much moisture, so that might be good. Particle shape is important, so if you think of lactose, if you have spray-dried lactose, it flows very well, and so forms good tablets, but crystalline lactose is not so good. There's a mixing and stability of mixtures, and part of the mixing, one of mixing theory is actually to use ordered mixing, where we use particles which actually have a very high surface roughness, almost spiky, I suppose, in my mind, but where little particles can actually fit between these surface irregularities and hang on to them. So that gives you a good way of mixing things. But so if you don't specify your particle shape for your carrier particle adequately, you aren't going to have the fine particles sticking to it, and then the formula won't work properly. Packing properties I'm going to come to a bit later. Right. How can you evaluate and control powders? I'm just going to talk about a few things today. Particle size and shape, flow and packing properties, and a little bit on segregation as well. So let's start off with particle size. And Yogi Berra, the American baseball player, had these marvelous little quotations, but one of them I've heard quoted before, which I love, is actually you can see a lot by looking. And my first boss used to say, have you looked under the microscope if anything went wrong? And so he was Geordie, so it was quite a tough way of telling me. So after a few times this, I always used to look under the microscope. And it's such a good way of actually knowing what's going on. So there was an analgesic tablet where it was one of the sweetening agents in there. The supplier changed the site of manufacture, and unbeknown to us, it changed the particle shape. And for whatever reason, the tablets would no longer form good, robust tablets. And so, but microscopy identified that problem very quickly. Do you think we need to look at particle size or a particle size distribution? So this is important in specification. So if we have a specification, a QC specification that says 90% of the particles need to be less than 100 micron, but then you have some new suppliers offer you material. Are you likely to get the same material? So in an instance I can think of, the original supplier actually had a medium particle size of 50 to 70 micron. But the new supplier, which they said, oh, we meet your spec, had a medium particle size of 10 to 20 microns. So clearly, although they both met the spec, they were actually very different particles and very different flow properties. And so that specification wasn't really adequate. I can't talk about particle size methods today, there's not enough time. But I will just say a bit about presentation of particle size distribution. I've seen occasions where people just have a simple Excel bar chart of weight of particles on each sieve or percent of total weight, and that isn't really that helpful, really. And what we really want to see is some kind of cumulative weight over size plot of its particle size, so, or cumulative weight under size, and that actually can help you compare batches or different materials very easily. One thing to watch out for is actually, have you got a weight distribution like we get off a sieve, or is it a number distribution? And if you're a yokel, say from the Isle of Wight, you might say, I'll have 2 kilograms of those potatoes, please, and make them all small ones so I get more. And really, that's the difference between a weight distribution and a number distribution. You need to be very careful when using means, medians, or modes, and what sort of distribution it is, whether it's a log or a normal distribution, a log or a simple arithmetic distribution. And at the bottom I put a reminder that as particle size decreases, powders become more difficult to handle. That's just a little reminder that finer the particles are, the more difficult things become to handle. Now I want to show you a few distributions. So the question is, can all these distributions have the same mean particle size distribution? So just look at these two to start with. So looking at these 3 to start with, I'll stop just there. So in the center red one, there's quite a tight distribution. The blue one shows actually that there's more fines and more coarse bits. So does that really matter if you have more coarse particles or more fine particles? It might do in a certain processing. And the purple one is actually a bimodal distribution, but they could all have the same mean particle size. And if it was a weight distribution, they probably come out the same mean particle size. How about this next distribution? So this actually could also have the same mean particle size, because this could be presentation as a number distribution. So if you think about a sieve analysis, you might only have a low weight of particles on the finest, left on the finest sieve, but there'd be lots and lots of particles compared with a few particles on the big sieve. So it's actually important to think of number or weight distributions. Next slide, please. Oh yeah, and that just shows you that some of them are weight distributions, some of the number distributions. Right, let's talk just briefly about flow and packing. Well, there's bulk density, and for those of you who don't know bulk density, one little click will actually reveal all. Can you get a click, David? Thank you. Oh, thank you. Yeah. So bulk density is really the weight of powder and divided by the volume of powder, and usually we call it in grams per centimeter cubed. So really it's the weight of the powder particles divided by the volume of the particles. But not just the particles, it's the particles plus the air spaces between them. And bulk density is actually such a useful thing, because it can be from, are you likely to get all your product into a container, which is actually pretty important. If you can't get everything in the container, you look pretty silly. Or it might actually be something like a tablet die. If you can't get all your powder into a tablet die, you've got a bit of a problem there. But you can also extend it to actually use it as a flow indicator. So there's things called Carr's compressibility index and Hausner ratios, which actually seem to equal flow properties. So I think it's a derivative of particle size and shape and surface characteristics and surface roughness. So it's actually quite a good, quick, simple way, quite reproducible too, way of actually assessing some kind of measure of flow. Other ways you might measure flow are just to pour a powder through a funnel and see how long it takes. But you should think about the end effects, which is really good for free-flowing powders. But usually they're the last ones you actually want to measure because they flow freely. You don't need to measure the flow rate, so it's not very good for non-flowing powders. Similarly, for angle of repose, and there's a little diagram of it there, so you can have a nice cone, which you do get with free-flowing powders, of course. But as they become worse and worse, you get like a cone with a sort of chimney in the middle. So what is actually the angle of repose? I guess shear cells are actually the gold standard, and they are based on strong powder technology, powder mechanics principles. And years ago, they used to take about a week to determine the flow around one particle. I know because I did it. But I think they have become automated now, so they're probably much more useful. And as I say, the basis, they're actually on sound mechanical principles. And recently there's been the powderiometers, which I think also are really good for comparing particles and things like that. And you can get quite a high throughput. I'm not sure how they relate to pure powder mechanic principles, but at least they are actually easy to use. So the next bit I want to talk about is separation and segregation. And how does it occur? So segregation usually occurs when particles in a mixture have a different size or shape, and density is generally reckoned to be a minor cause. And really there's four main types of segregation, I think. So there's this one where larger particles have more momentum and therefore travel further, and the posh name for that is trajectory segregation. And I've tried to do that with the bucket on the side where the blue and brown particles are falling out. Because the blue ones are bigger, they will tend to roll down the side, and so you get separate layers of brown and blue. The sieving segregation, with fine particles will actually fall through the gaps between big particles. And there's fluidization and dusting. So if you had your dusty muesli and you shook it all up to mix it, you may find there's a layer of white powder on the top. I can remember having a blue granule-based product in a mixer once, and we mixed it all, and then we left the lid down while the dust settled. And lo and behold, when we opened the lid, it was actually a white surface on the powder. It was a bit of a shock. We were expecting it to be blue, and that was a separation of the white of the fluidized particles. And then we know about the rise of coarse particles on vibration, which is mentioned in the muesli earlier on. So how can you measure segregation? Well, there are a few actual official methods. There's a segregation measurement tester from this Material Flow Systems Incorporated, and then there's one that actually looks at air in train to find. So this is the dust that's in the air and then settles down later versus the bulk powder. And there's a company called Jenica and Johansson who actually promote that. But really, you can think of your own method, and the important thing with all this is actually to choose a method that actually will be applicable to your situation. You can always get a powder to segregate. If you vibrate a powder, it will segregate. So it's actually really important to choose the right one. The other challenge is actually how to sample the sampling. So you take your sample, you give it to an analyst, who then has to take a spatula and take little samples out of it. So another opportunity for segregation. So sample splitting is actually very important to consider. And this, the last little bit is actually, what do you do when particles you buy aren't how you want them? We can change the particle size by milling. We can sieve them, but I don't know what you do with the bits that you sieve off. You can modify surfaces by removing sort of moisture or neutralizing the electrostatic charge, and then we come into the formulation science. This is where our formulation skills come in, where we can have flow aids or moisture scavengers, or go on to further processes like granulation, which is probably a talk for another day. So just to finish off with, there's a few summary points at the end here. Making formulation from particulates is always a challenge, and the properties of powders aren't always easy to define, but there's some key parameters that can be quickly and easily measured to help us understand them. And just when you're formulating a product, it's actually important you understand what you're making and why, to make sure you measure, so you actually make a product that the customer actually wants, and you can work out what the critical quality attributes are to fulfilling this customer promise. And you need to think about what needs to be controlled and how it's to be controlled. You can measure everything, but you don't need to measure a surface area of everything or moisture content of everything if it doesn't irrelevant to the purpose for what it's for. So you need to consider that. So it's important to use the right tools at the right time to build the product understanding. So you might take some more measurements, do full particle size distributions and development with a view to actually having a simple specification for our QC in the end. So I'd like to say that an application of a structured approach to product formulation will enhance your and your business's productivity, which I think is what we're all about. Thank you very much for listening.
Well, thank you, Ian, and thank you for that whistle-stop tour through the mysteries of powders. I'm always amazed how often you're able to relate everything to the science of muesli. I did say before we take some questions, and if you do have some questions, please could you use the chat or the question function on GoToWebinar. I said I'd come back to iFormulate Consult and just talk a little bit about the ways we help companies. So on this slide you'll see some of the questions we often get asked in terms of people want new ideas, or they want to understand the pros and cons of the technology, or what markets they want to go within their technology. We do simple problem solving, and you may have a problem with powders and it may be ourselves, or we may be able to use Ian to solve your problem with a powder or to develop a new formulation based on a powder. And of course we can do in-house training, customized or the open training courses. Also on this slide, when you get a copy, you'll be able to link through to our website where you'll see some examples of what we do for consulting. We're often asked though, well that's all right, but how does it actually work? Well, the way it normally works is a client would provide us with a brief. We're used to working under non-disclosure agreements, so we'll have a further discussion to get more details and drill down into what are the critical, I guess, quality attributes of that brief. We then tend to provide a proposal and a quotation which gives the approach, the deliverables, the timescales and the fixed fees. That's often staged, and we normally have a mid-term review to make sure that we're on the right track, and then we submit a final report with supporting information. And we have a meeting which can be in person or can also be over the web using something like a GoToWebinar or a GoToMeeting type of function. If you are interested in these type of topics, please get in touch with us either through info@iformulate.biz or via our personal emails, which again are on the website. So I'm aware that we're very close to time, so you're going to remain on mute. If there are any questions, we'll either take them now or we'll answer them afterwards. As I said at the beginning, you will be sent details of how to access this recording and the slides used in the webinar. Ian did mention a Design for Formulation webinar that he ran for us just about a year ago, and there's a link on this slide to that webinar. Our next one in the series is on adhesion, a sticky problem, and that will be on Thursday the 15th of September. At 1 p.m. UK time, and again you get details much nearer the time on how to register for that, and if you want to listen to previous webinars, they're all under our training and events. I can see actually we've come to 1:30, so what I'm going to do, rather than take questions, if you do have any specific questions, please feel free to email us, but I'm going to end this webinar now and wish you all, thank you for your attention and wish you all a happy day. Thanks very much. Goodbye.